the time of abandonment of the fan, and so we get that as the age for the offset. And so it's pretty crude, but we get about 7 millimeters per year. There's a couple other strands, parallel strands, or maybe some deformation on there, so you get about 8 millimeters per year, 8, 9, something like that. When we look at other studies in the area, ours is in red here. Sorry, that's kind of hard to see as well. But we're kind of right in there. So we're about 10 millimeters per year. It's a pretty good number. It matches some other studies, and we've sort of validated it, verified it at this site. So then quickly, a couple other interesting features. The northern part of the Alaska Range is the northern foothills fold and thrust belt. This line right here is a profile. So here's that profile. So it's a bunch of thrust chord anticlines, and then the anagravel, which is a plio-pleistocene unit, dark gray here. Previous studies suggest about 3 millimeters per year across that entire system. And here's a picture of a scar, a Holocene fault scar on the front of that system. Pretty poorly constrained so far, though. But this is just showing you that we need there's a lot more work to be done in interior Alaska. There are some faults seen in LiDAR data, such as these right here that cut through the gravel pit along the highway. They show up really well. These are about 17,000-year-old outwash terraces. Put the faults in there for you so you can go back and forth. Now the one at the top here, we don't see that one in the LiDAR. So we think it's either a fold there or just, maybe the deformation is being accommodated on back thrust. Because those faults all face to the south. And there's where they are. There's the geologist standing on the scarp. It's only about a meter high, so you don't find it when you're walking around the woods. If you trench these things, you get some typical thrust fault, reverse fault, stratigraphy, drag folds, and sort of overthrusting of the sands here. This is the log of this wall right here. And Ellie worked on this trench. We got some dates in here, radiocarbon. And this is a lust, this orange unit is a airborne lust, and they're about 5,000 years. So basically we had an earthquake prior to about 5,000 years with just a small amount of displacement. Just barely enough to warp the surface. But there was a good, 10 meters of folding or so, and about 50 centimeters or so of thrusting. So I think the slip rates for this little back thrust is about 0.02 millimeters per year. So given the age of the surface. So taking that, it just suggests that the northern foothills fold and thrust belt has a lot more deformation occurring on other structures. This is just a small part of it. So we've just cracked the beginning of it, understood. So then finally, you get up into the deep interior Alaska. The Caltech-Tuntina fault system is a major fault system. It goes all the way across the state almost. There's several places on Google Earth where you can see evidence for possible surface ruptures. This line of green right there, and then along the Caltech, this helicopter shot. But very poorly documented, and it's just really unknown. There's no studies on slip rates. The geodesy is too sparse to put any constraint on slip rates, and the geologic studies, they don't exist. Where we look along the highway on LiDAR, there's a couple faults. So these two images kind of occur in these little red boxes. So they're kind of in the junction between these two faults. There's got to be a connection in there somewhere. But the evidence is really weak. There's some linear valleys and some saddles in the ridge lines, but it's really weak, and you don't really see much as far as offset surfaces. But seismicity indicates that they are. So they probably are. But what does it all mean? If you take all those observations, so this is about 5 years, about 30,000 miles in a helicopter to get this information. Alaska is very remote, and it takes a lot to get there. So we're doing 5,000 miles a summer to find these things. But there's tons of faults, and there's a lot more to do. But my main premise is that if you're really careful and you look for the major faults, you're going to capture most of the deformation. So here we have 50 millimeters per year, about roughly, of subduction, Pacific plate under North America. And if we do the same thing we did in Nevada, we see we have about 35 millimeters per year being accommodated across the Chugach Range, the St. Elias Range, the Wrangels. And then you can add in, say about a millimeter per year of northwest directed compression across the Castle Mountain Fault. And then across the Alaska Range, you get about 10 millimeters per year of the Denali Fault, maybe a millimeter or two on the southern foothills fold and thrust belt, 3 millimeters per year or so on the northern foothills fold and thrust belt. And then once you get up into interior Alaska, you get the slip rates are smaller than what can be detected at the threshold of geodetic networks. So we have probably less than 2 millimeters per year in the kind of interior of Alaska near Fairbanks, and probably even less up in the north. So similar to Nevada, you have 3 millimeters per year or so, a similar distance from the plate boundary. So you get this deformation that is extending way into the North American plate in both of these major tectonic areas. And in Nevada, we have no vegetation, we have easy access, you can really get there and do the nitty-gritty work on each and every fault. In Alaska, you have a lot of permafrost, you have tussocks, you have vertical growth of the soil, you have all these things. You have lust that blanketed the entire interior of Alaska right after the last glacial maximum. Tons of lust buried everything. So your chances of finding a good paleoseismic site where you can really characterize things are pretty tough. But nonetheless, if you go through and systematically go through the state, you can basically match the geodetic rate with geologic studies. So large uncertainties exist in both geologic and geodetic rates in interior Alaska, but and the rates are extremely low, but you still have the risk of large earthquakes there. This is just a frequency plot of the number of earthquakes per annum for different magnitudes, and it just suggests that the frequency of magnitude 7s in interior Alaska is greater than 2,000 years. So with that amount of time between earthquakes, your chances of preserving any kind of fault scarp on the surface is pretty low, especially in such a dynamic environment such as that. So I'm not going to read through conclusions. I'm just going to show you this picture, which is awesome, on top of the foothills fold and thrust belt. I'll just say that if you're careful, you can really, the total strange budget can be resolved by geologic studies, but that careful documentation of all the active faults is really necessary to completely resolve that and to match the geodetic rate. And then here's the top of the White Pine Range. And so similarly, the Pacific North American strain budget can be completely resolved with geologic studies, give or take a millimeter or two per year. All the major faults in central Nevada have had late Pleistocene earthquakes and are capable of generating major earthquakes in the future. So although the slip rates are fairly well resolved, and we know what's going on pretty good with that. Slip rates are used in seismic hazard models. There's still frequency and timing of large earthquakes is really poorly constrained, and that's the subject of my current research, is trying to get ages on a lot of those earthquakes. So with that, I'll conclude. Thanks so much for having me. I'm happy to entertain any questions you might have.
What is the sense of motion for the